Hello everyone. Welcome back to Class 12 Mathematics. Let me start with a small thought. Imagine drawing a curve on paper, slowly and carefully, but this time you are not allowed to lift your pencil even once. If you can complete it smoothly, that's continuity in action. Continuity is the backbone of calculus. Without it, the whole idea of limits, tangents, and differentiability collapses. Today, let's explore this beautiful idea step by step. So, what exactly does continuity mean? A function is called continuous at a point if its graph has no gaps, no jumps, no sudden breaks. Formally, if you can trace it smoothly with your pencil, it is continuous. Mathematically, we say limit of f of x as x approaches equals f of a. I'll say it symbolically. Limit as x tends to a of f of x equals f of a. Equation 1. This is the formal test we'll keep coming back to. Now let's make it precise. For a function f from real numbers to real numbers, f is continuous at x equals a if three conditions hold. Number 1, f of a exists. Number 2, the limit of f of x as x approaches a exists. Number 3, that limit equals the actual value f of a. And remember, the limit must exist from both sides. That means limit as x approaches from the left equals limit as x approaches from the right, and both equal f of a. Equation 2. If even one condition fails, continuity breaks down. Okay, but continuity is not just about a single point. What about an entire interval? On an open interval, a, b, f is continuous if it is continuous at every point inside. On a closed interval, we need one-sided limits at the boundaries. That means limit as x approaches from the right equals f of a. Limit as x approaches b from the left equals f of a. Formally, continuity on is written as f continuous on if and only if three things hold. Right continuity at a, continuity on the open interval a, b, and left continuity at b. Equation 3. Not all functions are lucky enough to be continuous. Let's classify discontinuities. First, removable discontinuity. Here the limit exists but doesn't equal the function's defined value. For example, sin x by x at x equals 0 if we define f of 0 as 0. Second, jump discontinuity. Left-hand limit and right-hand limit both exist, but they are not equal. The function literally jumps. Third, infinite discontinuity. As x approaches a point, the function shoots off to plus infinity or minus infinity. Each type tells us something important about the graph and possible ways to fix the function. Here comes the good news. Continuity behaves nicely under algebra. If f and g are continuous at a point a, then their sum, their difference, and their product are also continuous at a. If g of a is not equal to 0, then f divided by g is continuous at a. And the composition rule is powerful. If g is continuous at a and f is continuous at g of a, then f of g of x is continuous at a. In short, continuity is preserved under addition, subtraction, multiplication, division, and composition. Equation 4 shows it clearly. Limit as x tends to a of f of x times g of x equals limit of f times limit of g. Let's prove continuity with a simple but classic example, sin x at x equals 0. Step 1, f of 0 equals sin 0, which is 0. Step 2, limit of sin x as x approaches 0 equals 0. Step 3, both values are equal, so all conditions are satisfied. Hence, sin x is continuous at 0. In fact, sin x is continuous everywhere on the real line. The smoothness of the sine wave makes it a perfect example of continuity. Let's quickly wrap up what we covered today. Continuity at a point needs three things: the function must be defined, the limit must exist, and the limit must equal the function value. On intervals, one-sided limits handle the edges. Discontinuities come in removable, jump, and infinite varieties. And continuity is preserved under algebraic operations and composition. Finally, we saw that standard functions like polynomials, sine, cosine, exponential, and logarithm are all continuous on their domains. So, continuity is the foundation that makes differentiability possible. And in the next video, we'll take the natural next step, differentiability, and how continuity ensures smooth slopes and tangents.